Good morning, and thank you again for joining today's live demo of accurate automated item picking for retailers. My name is Lisa Shaw, and I'll be your moderator. I work on the marketing team here at SICK, and I'm excited to be hosting today's session. I'm also pleased to introduce today's speakers. Nick Longworth, he's a senior robotics engineer for SICK, Sensor and Safety Integration Team. Nick joined SICK in 2019 after gaining over 7 years of experience in the automated engineering and machine building fields. Brian Duncan is a national sales manager for retail distribution at SICK. He joined SICK in 2018 with over 20 years of experience in the supply chain and intralogistics industry. Bruce Muir is a director of distribution automation. He has 30 years of experience in the automation systems deployment and retail distribution. In this webinar, you will learn what is PLB. You'll see a live demo of the PLB and polybag item picking applications. You'll learn how the PLB can address the impacts of COVID-19 related labor shortages and reduce labor costs, and so much more. Before we get started, I want to share that a recording of this webinar will be emailed to you following today's presentation. Also, feel free to ask questions at any time throughout today's event by typing your questions into the Q&A box in your control panel. We'll take some time at the end of today's presentation to address as many questions as time allows. Lastly, please place your webinar display in the side-by-side view as shown on the current PowerPoint slide. Our presenter will be showing you a PowerPoint as well as some live video during today's presentation. Now let's get started. Nick, Brian, and Bruce, please take it away.
Good morning, everybody. I'm Brian, and I'll kick off the webinar. Before we get into the heart of the material, I want to tell you a little bit about SICK. We're a leading global supplier of intelligent sensing technology. We manufacture our devices principally in Germany with plants in the US and Asia that serve to support these markets. We focus on three main fields: factory automation, which is any type of manufacturing, including automotive; logistics automation; and process automation, which serves much of the gas, petroleum, and petrochemical market. Advance, please. So the content for this webinar is born from our logistic automation focus, which includes parcel and postal and several other initiatives. But today we're going to more finely tune to the retail distribution and fulfillment operations. Advance. So today we're going to talk about picking with robots. SICK provides the enabling technology for these kinds of applications, and Nick will go over that in detail and do a demonstration shortly. So robotic item picking has been developing for many years and is deployed in thousands of operations in many markets. Logistics, however, has been and still remains a challenge, right? Justifications haven't changed, though, and have actually become more acute, especially during the pandemic. Some of these are the shortage of labor, repetitive tasks that are not value add for an associate to perform, and the safety of associates, which include interaction with machines, and in the COVID world, the need for distancing. Some applications which are still under development and are getting close but are not quite ready for scale are piece picking from bin shelving, case picking from an AMR, or goods to robot picking. Cost, speed, processing horsepower are all factors in this. Now, the enabling technology that we're going to talk about already exists for these types of solutions, and that's what we're going to talk about today. Advance, Nick. There are some applications now, though, that have emerged which are able to be deployed at some scale. These include mixed case palletizing and depalletizing. Examples of where you would use this would be inbound at an import facility for case handling or pallet handling, or outbound to stores where you'd be palletizing a mixed case load that needs to go to a grocery store or out of a food service distribution center. Those are a couple of examples. In these types of solutions, what we do is provide the technology to help identify, locate, singulate, provide guidance for the head, and provide collision detection for the head. Second thing that we see that we think there's a real opportunity is in unit sorter induction. There's two basic things that we see happening here. You either bring a bin or a tote of with multiple SKUs in it that you will pick clean, place on the sorter for sortation to a destination or to an order. Or in other cases, you might bring a bin or a container of a single SKU to the sorter. You'll pick a certain number out, place it on the sorter for sortation, and then send the remainder back to storage. Now, in this operation, what we would do, our technology enables the solution to identify, locate, and provide guidance. And then the third one that we see emerging now is container loading, unloading with robots. You'd see this at the inbound of an RDC where you're getting in a container load of cartons that have been floor stacked and they need to be singulated and palletized. Or you would see this outbound to a store or to a cross-dock operation. Again, in this application, we provide the technology to identify, locate, singulate, and provide guidance and collision detection. Now, I'll hand this off to Nick. He's going to talk about how we enable robotic item picking.
Thank you, Brian. So, with that in mind, how do we actually get started with item picking? And that involves our product called PLB. What is a PLB? It means part localization in bins. You don't actually need a bin. It's really just 3D part localization. You can have a static area. That's fine too. But the main idea is it is an enabling software. It combines some of our 3D cameras with localization algorithms and support for robotics with collision detection and everything you need to make your application work properly. So this is what a PLB system actually looks like. You'll have the robot in question. It could be multiple robots. It could be one robot. It's up to you. You're going to have a vision sensor. And that's going to be, in the case of PLB, one of 3 sensors that you'll see in a slide or two here. And then your vision sensor will go back to our PLB software. So it'll be directly wired to a computer which handles the processing. That computer is going to, again, run your PLB software, and it's going to be linked to your robot. The software is the same regardless of which vision sensor you end up using. So the PLB engine is what we call it, is actually a modular software. So we can, substitute different algorithms, different cameras, different types of robots. All of it can be into the one software. So you'll see under image acquisition, we have those 3 different cameras there. Under our localization algorithm, we do have multiple algorithms. Today, we're going to be talking about 2 different plugins, which are our pipe plugin and our flat region plugin, which I'll explain in a little bit. We do have other algorithms, such as our surface algorithm, which is our CAD matching. We have Edge, which is our 3D pattern matching, among many other plugins. Just so everyone knows, a plugin is essentially a third-party algorithm for PLB. PLB does not require the localization algorithm to be built into it. It's something that a user can build themselves in C++ using PCL, Halcon, OpenCV, any vision library they want. We have a few that we have built and maintain ourselves, like the ones we're going to be seeing today. But the main idea is that it is an open localization system, and then you can use PLB for its other functions, such as collision detection and robot communication and everything else. So these are the 3 different cameras that PLB can possibly use. We are adding more as time goes on, but these are the ones that are built into the software currently. Each one has a purpose, and it solves different applications. So the main idea here is that we're going to be able to use the most advantageous camera technology for the application. We're not going to force fit our camera to the application. We're going to force fit the application to our camera. So In the case of PLB 500, this is a laser triangulation camera. It'll sweep a laser across your volume of view, and it's going to watch the deformation of that laser to build your 3D point cloud. The main applications for this are large volumes that maybe have issues with ambient light, maybe have some issues with reflection, so metal, cheap metal ingots, that kind of stuff. Very good for this camera. PLB 520. This is our high resolution multi-volume camera. So this one is the one we do small parts with. We do any sort of really high resolution needs. It is flexible, so we can do small volumes, big volumes. We can change the calibration on it, how we see fit for the application. And then we have our Visionary S, which is our PLB 510. This is our high-speed camera. So it's also structured light, just like the 520, except for its passive structured light. So it's going to be very quick. It does 30 frames a second. And so that's where we really look to use this one. Is you'll see it today in logistics and that area. We'll end up using it a lot because you need the speed in those applications. With the 510, we can generally get cycle times down in the 0.2 second range, or even faster if we need to. So again, the algorithms we're going to be looking at today are, one of them is the flat region algorithm. This one is for finding any sort of flat area of arbitrary size. So if you're looking for boxes, bags, anything like that, you're going to be able to find it with this one. So parcel sorting is a good application, parcel singulation, and order commissioning. And so the idea with this particular algorithm is it's going to locate areas where the 2D pixels seem to connect. So it's looking for logical clusters of points, essentially. And the object doesn't have to be completely flat. There are parameters built into the algorithm to allow for curvature, which you'll see when we pick some bags later here today. The other one you're going to see, the other algorithm, is our pipe algorithm. So this is finding anything with a cylinder sort of shape to it. So when we're trying to, the typical application we see for this is any sort of high-speed piece pick. And obviously it has to be a cylinder-shaped object. So in the case of the picture you see here, we're picking pencils in terms of a piece pick here. And the operating principle for this is we're looking for local maximas in the image. So we're looking around the image and looking for where you see a curve, and then finding that local maxima for that curve. Once we've found, the number of them that we can find in the image, we're going to look and see which ones are logical to connect together. And so then you'll combine those ones that you can connect together and compare it to your parameters, which give you your length and your radius of your cylinder, and see if they compare favorably. If they do, it's a part. So that's how that one works. Last thing here, and we're not really going to go over this in depth today, but just so you know, the integration with a robot with PLB, it's fairly simple. There are two different things that go on here. The first is actual just communication, and that's going to be an ASCII-based TCP/IP interface. We do have sample code for most robots that we can give you and let you use to build up your application. But it's basically going to be TCP/IP socket messaging. We can support XML or CSV, and there's all sorts of different commands that can be customized to the interface that you want it to be. It's very flexible, which allows you to solve many, many, many applications instead of having to be force fit to whatever commands that we choose for you. And then the other thing about robot integration is going to be the hand-eye alignment. So PLB actually gives you the coordinates to go to. You don't have to do anything with them. You can literally just go to the coordinates PLB gives. And in order to do that, PLB has to understand what your robot's hand-eye alignment is. So it has to know what the coordinate system for the robot is. And to do that, essentially, if you see in this upper right-hand picture here, you'll have a cone that you attach to the robot. It doesn't have to be that big. You can use any size you want. It could also be a sphere in some cases. And you'll take a tool center point for the tip of that cone. That tool center point is important because the camera is going to take an image of that cone in a certain number of locations, and the robot's going to report what that tool center point is at that location. From that information, PLB can build a translation between its coordinate system and your robot's coordinate system. That allows it to give you your points in the robot's actual coordinate system, so your robot can just go to the part itself and not have to do any post-processing on the robot controller. So that's all it really takes to get PLB working with the robot controller. So we're going to jump into the actual live demo here. So we're going to, on Brian's topic here of pick clean multi-SKU along with some single SKU applications, we're going to look at both of those today. So I have I have 3 different applications I'm going to show you. The first is a bag application that we're going to run through all of PLB with, and you're going to see exactly how to set this up, how it works with the robot, and see it move here. Then we're going to look at pencils and boxes, and those are just a video that I'm going to show you, but we'll take a quick look and at least show you exactly how this works and that it works very efficiently. So in order to actually start, we'll have to go to Configure up here in PLB, and you'll see a lock button up here. That actually is how we lock down our program in our PLB system. So when it's unlocked, we can edit things. When it's locked, we're ready to go for the robot side of things. So we go left to right in PLB here. You'll see these tabs over here, and we're going to start here with localization. So we'll localize our part, we'll set up our gripper CAD, we'll set up our poses, we'll set up our bin, and then our communication, which is already set in this case. After that, we'll be able to go to Analyze, and we'll be ready to go with the robot. So the first thing I do here, I'm going to go ahead and select my algorithm. In this case, I'm using my flat region algorithm, which is again a plugin into PLB. I do have many other algorithms I can choose from. In this case, this is the best for this particular piece. When I'm using a plugin, the parameters are not in PLB. We don't see them in PLB here. They're actually in an XML file because, again, a plugin is a third-party algorithm that isn't built into PLB. PLB is just running it as a C++ DLL. So they end up in a separate XML file that your plugin references when it runs. So this particular XML file is what I'm using for these bags. And for 6 plugins that we build, we generally have the same setup in all of our XMLs. Obviously, if a user builds their own plugin, this could be look very different. But with 6 plugins, you'll see generally this setup where we have filtering parameters up here where we're looking at things like how rough is the surface, how much noise will the surface have, the curvature of the surface, anything like that. And so this is very important because you have to tune it into the type of part you're doing. If I'm using a box, that's going to be a very smooth and flat surface. I don't have to have much curvature. There's not going to be much noise. I'm pretty good in that case. But in the case of something like a bag that we're going to be looking at today, there's a bit more roughness, a bit more noise. There's going to be a lot more curvature because the bag can sit any which way. It's very flexible in this case. So you'll have these. You'll want to set them up according to your particular part. So after that, you're going to look here at our rectangle settings. So in the case of the flat region algorithm, we're looking for a range of possible rectangles. We do have other algorithms such as predefined box that look for just one size. But in this case, we have a min width and a min length, and then we'll have a max width and a max length. And those are going to determine, if the flat region that it finds is in fact something we want to try to pick. If it's outside of these bounds, we're not going to try to pick it. And so the reason we're using flat region for these parts is with these bags, we're just looking for a logical surface to pick. We're looking for just some flat surface, anything that is flat to pick on. We're not actually locating the shirt that's in the bag or anything like that. We're just trying to get everything out in a singular fashion. We will be able to see the difference between bags, and that's because of this parameter up here, our neighbor radius. That's going to help us to understand where the creases between the bags actually end up. Keeping that low is the real key here. But at the end of the day, we're really just looking to pick on any flat surface we could see, and that's generally going to be just one bag, and we'll pull it out of the bin on its own. So after you found that rectangle, you'll have your confidence settings here. You'll have a density and a rectangular weight. Your density has to do with how many points are clustered together. So what's the weight for that? And then what's the rectangularity of those points? Are they circular? Are they more of a box? Anything like that. In this case, again, because it's a bag, I'm going to prefer the density of the points over the rectangularity. I generally am not going to see a super rectangular area because, again, it's a bag. It's going to be very flexible in this case. The last thing for setting this up is going to be the priority settings. So I can use the algorithm's priority, or I can use a different priority if I want in PLB. In this case, I want to use my algorithm priority because it knows more about what's going on. And so the algorithm itself, we're looking at our height, our planar, our confidence, and our centered priorities. The height, pretty obvious. How high is it in the bin? And how much weight do we want to put on that? Planar is how flat is it to the bin? So our XY plane along the bottom of the bin, how close in parallel is it to that? Confidence all comes back to these settings up here, our density and rectangularity, and then our centered weight, how close is it to the center of the bin, the localization that we found. All this adds up to tell us which of the localizations, because we're going to find more than one. We're going to find, maybe 5 different good spots to pick. Which one do we actually want to use? That's what this priority does for us. So to make this a little more visual, I'm going to turn on what we call debug view down here. So I'll set this to true. I'm going to go ahead and save it. And so if I jump back into PLB and I run the algorithm, you'll actually see a pop-up where it shows us all of the different localizations that it possibly found. Now, to do this, I have to go to Analyze. And today we're using our Visionary S camera. So again, this is our high-speed camera. It's going to be very quick in terms of how we get our images. So localize my bin. I'm going to localize a part. When I do that, I have this pop-up here. And this pop-up is what the algorithm's actually doing. And so you can see all these different surfaces that it's actually finding. And these surfaces in green are the ones that it can choose from. Those are good surfaces. They meet all of our parameters. And you see it's actually chose one down here, which looks to be this right here. And so anything that's green, we're good to go with. And you can see again, we have multiple things to choose from. Our priority is becoming this one based on those weights we've set. You do see these ones in orange down here. Those are basically saying these are good according to our filter parameters. However, they do not meet our rectangularity parameters. So that 50 by 50 to 200 by 200 that I set, these don't meet that. They're going to be somewhere in the looks of it here below that 50 by 50 measurement. So that's how our algorithm gets set up. At this point, it's ready to go. If we actually wanted to see a numerical readout, we could use the debug log. That would actually give us a numerical readout, and we could understand with those orange boxes exactly how big they are versus our parameters that are up here, and we could adjust our parameters accordingly. All right, so after that, once you've been able to localize your system, you're able to find your parts, what do you do to actually pick them? So the next thing is we actually have to bring in the CAD of our gripper. In this case, I'm using a suction cup on these parts. You could use fingers. It just depends on exactly what you're trying to do. So I have a suction cup at the end of this. This suction cup I can change, depending on what I'm doing. I have several different suction cups. So I've actually set up my tool center point. This is what this is here. This coordinate system, when I bring in my CAD, it has to be set up at exactly the same spot as the tool center point of my robot. If it's not set up at that tool center point, then PLB will not understand how to properly rotate your end of arm tool. That will cause you to do all sorts of fun and interesting motions. So very important that this is the same as your tool center point on your robot, this coordinate system. So you see I have this just right on the surface of the fixture that's holding my suction cup. My suction cup will come out of here afterwards, and I'm just not seeing it because I could end up changing it, so I don't want it in there. And just by the way, the CAD model that you bring in needs to be either a step or an IGES file. So once this is in, you're good to go with and you're at the right spot, you're good to go, and you're ready to set up your pick poses. So in this case, I only have one pick pose. If you were doing surface, our CAD matching, or our 3D pattern matching, you would actually see your part in here as well. In this case, because I'm using a plugin, I don't have any data on the part because we're just doing some mathematical algorithm instead of a more visual algorithm. So in this case, I just have my gripper showing up here. I have this pose that it's sitting in here, and that pose is going to be how I pick my part. So I have a measurement of my my suction cup in this case, and I have it up high enough that my suction cup isn't going to go run into something on the way to the part. This is also how it does collision detection. So it's going to look at this CAD model and decide if it's going to collide into the bin walls or into another part or into anything else based on this CAD model. So not having my suction cup, I might want to add that in eventually, but in this case, it's working just fine without it. So you would end up moving this around to wherever you want your pick point to be. I then do my path planning. PLB gives you 5 different points with a result. It will give you a point above the bin. We call it an entry pose. It'll give you a approach pose, which is moving towards the part. And then we have the pick pose, a clear pose, and an exit pose. The clear is going to be departing the part and where the part is once you have it. And the exit pose will be the height above the bin again. So you can see here, I have my height above the bin set to 300. I have 100 for my approach, 100 for my clear, and 400 for my exit. My exit is higher than my entry because I'll have a bag, and that bag can be sagging. It can be God knows what orientation it's sitting in at that point because I'm not, it's a bag. It's very flexible. It's going to be pulled down by gravity. In addition to that, we have our collision settings here. For a plugin algorithm, the only collision setting we have is points. So it's the number of 3D data points that we are intersecting with in the image. So we'll take an image. When we start moving around the image with our gripper, how many data points do we intersect within that image? In this case, I have it set to 10, which is fairly low. If you're using some of our other algorithms, you may have some other options here as well. And we do look at our approach. So we aren't just looking at the pick pose and what it might be intersecting with. We're looking at everything, the whole motion that we give you. So last thing here is going to be our bin. So if we're actually looking at, in a case of having a bin, we don't need to have one, as I said. You can have a search volume where we're just looking at a static area that never changes, and we're looking at parts within that area. That's fine. In this case, I do have a bin. We set the parameters of that bin. I have a custom size in this case, and you'll have your X, Y, and Z parameters of that bin. This case matches my bin up here. The localization of the bin actually has to do with the rim. As you can see here, we can't actually see the sides. They're occluded. We can't actually see where they are. We can just see the rim. So this top wall thickness is very important because it gives us a good understanding of where that rim's supposed to be. So once we have this set up, we can actually set up some of our other parameters, such as the score threshold for the bin, the max width, length width ratio. This max width length width ratio is pretty important because your bin's going to probably be warped over time if you're using a bin. It's not going to be exactly the same. So setting that ratio a little higher allows it to deviate from its known location and kind of adjust itself to what it's seeing. So pretty cool thing that can really help in some cases. We also have the ability to build virtual walls. So again, because you can't see the wall, we actually build it based on the location of the bin. This can be turned off if you're using a search volume, for instance. So if you're picking off a pallet, not a big deal. We just turn off the virtual walls, and then you don't have any collisions because there's no walls there. Couple of other things going on here. Setting up your bin generally is pretty important. You'll have the empty search volume, how much of the search volume, how many 3D data points in the search volume are necessary to say that there's an empty volume, so you have no parts left. In this case, anything below 300 data points, 300 3D data points, anything below that is going to be empty for me in this application. Again, depends on the application, something you can set up. One neat feature here is zones. We can actually split this bin up into multiple zones. So if you have small enough parts that can be picked where you could basically say this is one bin and this is another, you're basically saying that if I pick a part here in my right side, my left side will not be disturbed. Then you can use one image and pick multiple parts with that one image. So just a good way for optimizing your application. So neat feature, just something to know about. There's a lot of these features for optimization in here. SICK has had the PLB product for 10 years at this point. So we've been adding features based on customer feedback for a long time. So there's a lot of features in here that are based on optimizations that customers have requested and we can do. All right, so from there, we're going to go ahead and go to Analyze. And the analysis actually gives us a chance to understand what's happening when we're localizing and finding these parts. It allows us to debug. Instead of having to guess what we did wrong, we can actually see what we did wrong. And so I already have my camera set up, and you can see this here. My Visionary S is what's actually activated here. And I can change my parameters for my Visionary S right from PLB. I don't have to go to Sopus or any other software to change these parameters. So I can take images right here. I can get a new image. I can localize my bin, which again says okay, it found my bin. It's it's in a good spot here. And then I can go breakpoint analysis for localization. So I can say just go ahead and localize a part and give me the feedback. And so in this case, I'm using a plugin, so there's not a ton of feedback. It'll give me the score. It'll give me the location. Most of the feedback is going to be in my plugin. But it is nice to be able to search around and actually see the different flat areas that it's finding. So you can see in this case, it's going to prefer this particular localization here, which is a good one. And again, what we're doing here is we're looking for just flat areas to pick on. Any flat area that we can get to is what we're going to pick on. We do end up seeing the difference between the bags. So you'll see this bag ends here. And so we won't end up trying to pick there. And it will be able to singulate those bags by doing this and be able to put them down anywhere you please. And so the next thing you can do for your breakpoint is you can look at your collision. So you can actually see the motions that PLB is expecting there. And then you'll see any sort of the pick pose collision details. So you'll see any of the possible collision points that it could be having. And right now I have 0 points of collision, which makes sense. I don't have my suction cup built into this CAD model. So it generally is not going to find much collision unless I'm about to run into the wall of the bin. So With that in mind, that's really all it takes to set up PLB. It's an easy software. It's quick and it's very, very powerful for anything you need to do with any sort of 3D robot guidance. So we're going to go ahead and everyone can see my camera here. I'm going to go ahead and let the robot run. It's going to come in. It's going to take a picture. In this case, the picture is taking about 0.4 seconds to take an image, localize the bin, and localize the part. We don't have to localize the bin every time. We could remove that from the cycle. In that case, you'll end up with about 0.1 of a second if you don't need to localize a bin. Or if you've localized it before and you're confident that the bin's in the same location, you wouldn't need to localize it again. So you'll see that happen. The robot will pick the part and it will put it down to the side. I don't have the most vacuum. I am using a small compressor, so you may see it drop the part in some cases. Having a little bit more vacuum would certainly solve that situation. I just have a small compressor in our office here. So you'll see PLB gets moved into run mode automatically by the robot, and then it comes in and it starts locating the part and picking it. You'll see there how it lost the part. It understands that it lost it. It's going to go ahead and try again on a different surface. It'll take a new image. So that really comes back to tooling, not to PLB itself. You see, this is a fairly strong process that we're doing here. It does find the parts, it does singulate them and pull them out of the bin. No issues. And it's able to determine that there's no parts left in the bin, and the robot goes ahead and moves back and waits for the bin to be refilled. So that is how you pick bags with PLB, and it's very effective, works very well, very quick. So next thing to look at here, we're going to look at some more singular parts and how we pick those. If you're just trying to do a piece pick for maybe packing or anything like that. So if I come back here, I'm just going to show you guys a video here of a pencil. So we have basically just a number 2 pencil, nothing special here. This is using our pipe plugin. So very similar to the flat region algorithm, we bring up the parameters in an XML file. And in this case, we set up the radius of the cylinder, which a pencil is actually a hexagon, but we can approximate it as a cylinder. And then we'll set up the length of the cylinder we want, along with some of our filter parameters that determine exactly how we determine what a local maxima is for that cylinder. Once we do that, it'll work. It'll find our parts. The main thing to know about this is the localization score is actually the length of the part that you find. So if I set my length of my cylinder to 100 millimeters and I get a score of 90%, that's going to mean that I'm within plus or minus 10% of my 100 meters. So I could be around 90 millimeters or 110. That's what that's going to mean for my score. So basically, you're not going to see the whole cylinder every time. It might be, occluded by another. It could just be in a corner, that kind of stuff. So you want to be able to have a little flexibility, and that's what that does. With the cylinder, the pipe algorithm, it does not have to be a rigid structure. So you could use a tube that has some flex to it, and this would still find it. It's still able to use its algorithm to be able to understand that there's a little bit of flex, and that's okay. So you'll see here, in this case, we're using our 520 camera. This is a much sharper image. It has much better resolution, as you can see. And we have some finger grippers here that come in and are able to easily pick these parts up and place them into another bin, which could be a package or anything else. This is, again, fairly quick. The 520 camera is a little slower than the Visionary S. This will end up being about a second, maybe a little less, maybe 3/4 of a second to get a localization. There's no reason you couldn't run this in the background of the robot and have it taking an image while the robot's dropping off the part. Additionally, the camera could be changed so it takes a quicker image, but you'll give up some resolution in that case. So again, that's how you do piece pick, and there's many ways to do that. Our algorithms can support many different styles of this. It's not just this one way of doing it. So if you had CAD, we could use our CAD algorithm. If you have a circle that you need to find, we have that as well. So there's many different algorithms we can use to do this sort of work. It's not just our pipe algorithm that can do this. So we're going to move on here, and this is more of a multi-SKU situation that Brian was discussing earlier. And so we have different types of boxes that are in this bin down here. You can see there are some boxes of batteries. There's some just sick sensor boxes sitting in here. And we're going to find all these and pull them out and put them down. We can sort them as well based on the size of the box. So our sizes we can actually know what the size is. We can have PLB report that, and we can sort it based on size. So in this case, we're using our Visionary S again. So this again going to be very quick. You'll see it's going to find the battery here. The batteries it'll go ahead and put in front. And we have our boxes that's going to put in back there. So again, this is going to use our flat region algorithm just like the bags did, except for in this case, we're not having any curvature. We don't want any curvature in this case because these are all very flat objects. The roughness isn't very high, anything like that. But again, same algorithm, very effective based on our parameters. And we could end up having the robot run multiple jobs. So we could end up, if we had bags in here and we had these boxes, we could have the robot or PLB run multiple jobs where we're doing one to understand that it's a bag and one to understand that it's a box. That is possible within PLB to run multiple jobs, multiple cameras, multiple robots, all of it's in there to be able to do very intense situations. So that is a brief overview of PLB, some of the ways we can solve your different applications. So that's just about everything here.
All right, great, Nick. Thanks very much. I have several questions here. So let me just hit them if you wouldn't mind. First question is, how do you time the drop to correspond with something like a loop sorter?
Something like a loop sorter, you said?
Yeah, we talked about picking up the parts. What about dropping it off? Can you put them in a specific location and at a specific time?
Yeah, I mean, that would be based on your loop sorter. So you would have a PLC or maybe the robot controller controlling that. Okay. And you could use conveyor tracking within the robot to help you with that. But there would be some sort of signal that you'd have to work with from the loop sorter equipment that would indicate to you when to drop off. We do have other sensors if you would like help with that we could work with you on doing that sort of thing. All right, great.
What robot brands can the software work with?
So the nice thing about TCP/IP is it is a generic protocol. So just about every robot can do socket messaging. If it can't, it can definitely do Profinet or Ethernet IP. So I know very, very few that can't do socket messaging though. So I would say just about any robot can do it. If it can't, what we can do is we can go through one of our SIM processors and convert everything to Ethernet IP or Profinet. I can tell you right off the top of my head, all major robot brands can do TCP/IP, and we have example code for all of those. So Fanuc, Kuka, ABB, Nachi, Yaskawa, Motoman, We have UR caps. So all major robot brands, you're good to go pretty easily. And if it's not, it's something we can help you through to get the communication working.
Great. Does the XML come included and scripted from SICK?
I'm sorry, in scripted function?
I guess what they're asking is the plugin that you're using for localization. Does that come with the software?
So when we sell the software, there are two different tiers that we sell it in. We have a tier where we say it's CAD enabled, so it's able to use our surface algorithm. That's a bit more complex of an algorithm because you're putting in a CAD model for localization, and it's using that to find your part. And then we have our regular PLB, which has plugins and it has the edge algorithm. And so we do provide those plugins as part of the purchase, and it's whatever plugins you need. We would be able to provide to you in that case, and that's that lower tier of cost as well. You're paying more for the CAD algorithm.
Gotcha. And the CAD algorithm would be something more like an automotive or something like that. Logistics, we see very few drawings of the product coming in.
Yes, CAD normally comes with complex 3D features like different assembly components for a car and that kind of stuff, or maybe a part that you're trying to machine in a foundry.
Right. Here's one. What if I have an array of bins that can have that can have cylindrical and or cuboidal objects together?
Okay, so if you had an array of bins, so there's a couple questions here. First, if you have an array of bins, we can switch between which bin you want to use. What we would end up setting up multiple bin profiles, and then you would command PLB to activate each one individually. That way you could locate it. So you can use multiple bins as long as they're all within the volume of view of the camera. And so once you find your bin, if you have multiple parts in there, we just run multiple jobs. So you would end up setting up, in this case, if you had cylindrical and rectangular parts in there, cube style parts, you would end up setting up a job that has a pipe algorithm and then a job that has the flat region algorithm. And there's two different ways to do it. One way is you could have the robot tell PLB which job it wants you to run first. So say, run my pipe job, give me results, and I'll go pick them. And then say, maybe after that, we'll run our flat region job. Or you can have PLB run both at the same time and give you the one with the highest Z or the highest score or anything like that. That is possible as well. So basically, you somehow combine those two jobs together in a logical manner for your application. So obviously, it can change depending on the application, but that would be, in general, the specifics to that.
In a case where that array was too large for a single sensor to see them, would you be able to look at would you be able to take the feed from different cameras in the same application?
So there's actually two ways to do that. Yes, we could end up using two cameras, which, by the way, you do not need to purchase the license twice. We do have what we call a secondary camera. So you could have two cameras set up, one for one volume, one for the other, and it would only need one license. So your cost wouldn't be super high in that case. So that is possible. You would end up setting up two different alignment profiles for the robot. So it would have a hand-eye alignment profile for one camera and then the other. The other option is actually to take one camera and put it on a shuttle or a linear slide or something and have it move around your application. And it'd be the same idea, is the robot would have multiple alignment profiles, that whole thing where we have the cone and we end up taking a few images and reporting the tool center point. We would have multiple profiles for the multiple locations of the camera. And as long as you report to PLB which alignment you're using, so where the camera is, it'll give you the coordinates that are correct for that camera position. So there are two ways to solve that.
Okay. Couple more here. What about plastic transparent zip bags with small electronic elements inside?
So that comes down to the technology you're using for the camera. So you'd want to, if you have those small electronics in them, one, it depends how many. Can we approximate it as if you have like 100 of them in that small bag, can we approximate them in bunches in there as a single object? But if there's just one of them in the bag, then we're going to want to try to figure out a camera technology that can see the bag instead of seeing the part inside the bag. And that's where it comes down to us having multiple camera options. Generally with plastic, if you hit it with polarized light, you'll see the bag, the clear plastic bag, instead of seeing what's inside. It'd be something that we would want to test more with your particular bag and everything. But we do have some options to try that out.
All right. It's great. Just as a little follow on, they said one LED in the bag.
Okay. Yeah. So if it's just one LED, we would want to test your particular plastic bag with one of our cameras that can do polarized light and see if it actually does show just the bag instead of seeing the parts inside the bag.
Great. Does it need to be a robotic arm, or could it be any other robotic configuration?
It can be anything you want as long as it can work with the software. So if you can only if you're using a 3-axis linear actuator and you don't need the yaw, pitch, and roll for your application, it's perfectly fine. PLB will give you your XYZ, and you can just ignore the yaw, pitch, and roll. As long as you can maneuver that cone around the space in order to give you the alignment profile, yeah, there's nothing that's stopping you from doing that.
Great. I have one more right now. It's, should the settings in XML be changed every time if I'm working with bins with a possibility of large numbers of objects to be present in it?
I'm assuming that means multiple types of objects within
Right.
it. Yeah. You could, it really, that's a hard one. It really depends on the application itself and what you have in the bin. If we could find a sweet spot where one algorithm, one set of parameters works for everything, that's great. It would be awesome. And it's happened before. However, if we can't, we might end up with 2 or 3 different jobs that we have to use and cycle through to get everything out of the bin. It really just depends on the parts and what we're trying to do. So it's a little hard to give you a clear answer there, but it's certainly a challenge we would like to accept. I can say that much.
Excellent. For those transparent bags, which technology? Triangulation, visionary, and X36? That goes back to the LED. Same gentleman who wants a question about the LED.
I would try the laser triangulation first because lasers tend to have some polarization to them. That doesn't mean that would be the end all. We would definitely try all of our possible options with it. We can also have different lights projectors on some of our cameras. So there's some other versions of the X36 that have different types of light. So it's something that, again, we would want to test more and try to figure out what works best of the possible options we have. I can't exactly say what will work off the top of my head. I would say that I would try the scanning ruler first, though, to see what the results are.
Okay. Can you talk just a little bit about picking speed, Nick? What we could expect in typical applications for picks per minute?
So the fastest application I have set up is 30 pieces per minute. And that's picking one part and then putting it down. So the picking speed will really be determined by how fast the algorithm can process. which is first determined by the computer you're using. So you get a really nice computer, it's going to process a lot. It's going to process a lot quicker. So in this case, we're getting 0.4 seconds per pick. If you can do multiple picks in the image and have a multi-head gripper, you might be able to get 50 parts per minute or 60 even, if you can actually set it up with that tight of a scenario. But just to clarify, the fastest I've actually ever set anything up is 30 picks per minute.
Okay. Well, that's what we have for questions right now. We have a few minutes left. If there's any last questions, please feel free to submit them.
Awesome. Thank you, Bruce, for moderating that. And thanks to Nick and Brian also for presenting today. Yes, if you have any questions too, feel free to message our presenters or type them into the Q&A box, and we will be sure to follow up with any remaining questions. And also thanks to our attendees for listening. For our upcoming webinars, you can visit STIC.com, and we have a list of our upcoming webinars posted there. So I think we can wrap it up. Nick, Brian, and Bruce, do you have anything else you'd like to say before we end today's session?
No, thanks for attending.
Awesome. All right. Thanks, everyone.